Yeah, we're going to continue in this chapter 6, which is a bunch of kind of tenuously related topics related, well, they're all connected to independent sets. Um, so, okay, so in this, on this topic, what I want you to think about is, imagine you're a spy. And you want to create like a sort of code language for communicating information. So you are creating a language of code words, okay, that you're going to use to communicate with your fellow spies. So let's say you have let's say the alphabet size is, let's say, n. So you've got like n distinct characters that you're allowed to use. So here's a basic kind of counting question. What is the maximum number of distinct kind of code words of length k that you could, I don't know, use, I guess. Okay, this is not a deep question. This is like a I mean, if you're someone who is an undergrad here or did their undergrad here, like this is like a basic math 222 question. So all I'm really asking is how many distinct words are there with an alphabet of size n, where the words have length k. So can anyone see what the answer to this is? It's not any kind of trick question. Yeah, I can see some people mouthing it. Yeah, so right, so it's just n to the k. We are making a word of length k. Each letter has n choices, so it's like n times n times n times n, k times, right? Okay, that's deep here. One thing I want to, because it's going to be useful for intuition later, one thing I want to kind of highlight here is if I take the number of length k words, or really I mean the maximum number of them, but I mean whatever, just the number of possible length k words. If I raise that to the power 1 over k, that's always equal to the number of letters. Because all I'm saying is n to the k to the power 1 over k is n, right? Okay, so yeah, if things were this simple, there would be nothing to solve. Here's the thing. So yeah, you're the spy and you're trying to make this language, and for whatever reason, you're communicating over some kind of a channel that has some kind of corruption, some kind of noise that corrupts the message as you send it. Okay, so yeah, so the kind of, I don't know, messages, when you send them, they can get corrupted. In very specific ways. So in the following way, so there's a graph there's some graph G with vertex set equal to the alphabet of your language, and for each edge, let's say UV in G, sometimes the letter U gets swapped to V when you send the message. So sometimes I actually send a U to whatever spy is on the other end, and this corruption in the whatever thing I'm sending it on, it sometimes changes U to V, and sometimes, so I'll say or vice versa. So this is a kind of symmetric relation that sometimes when I send a U, it changes to V, and sometimes when I send a V, it gets swapped to a U. Okay. As an example, imagine our alphabet is A, B, C, D, E. And maybe my graph G is a 5-cycle. So this is gonna turn out to be a really interesting case, the 5-cycle, and we're gonna look at it specifically on Friday. But yeah, so the idea is if I try to send the message A, D, C or something, you transmit it down this line, and things can get messed up. So maybe they'll actually receive the message A, E, D or something. Right, so maybe the first letter does not get corrupted. It just, I send A, D, C, and maybe they receive the first letter they've received correctly, it's A, but the second one, the D gets kind of swapped to an E, and then the last letter, the C gets swapped to a D, right? So it's possible I could send this and they might receive this, right? Now here's the thing, we need our language to not have any kind of ambiguity. So I don't want my language to contain two different words that can be confused with each other. So for example, these two words, if they were both in the language, and I tried to send this word, they might receive this one. And if I'm giving precise instructions or something, they may mess it up, right? Or if I send this word, they might receive this one, right? So kind of our rule for this language is that you cannot contain two words that can be confused with each other. So our kind of rule, if two words can be confused, then you can't include both of them. In the language. Okay, so now we're interested in, so a kind of problem is to find the max number of length k words that you could, that you can include, right? Yeah.
When you transmit a word, does the error happen independently of each letter? Like, would it do the different things to two different A's, or does it always do the same thing to different A's in the same word?
That's a good question. It's totally independent. So if I sent, for example, if I sent like AAA, it very well could be sent, they could receive E, A, B, or something. So yeah, anything can flip in any possible way. That's a good question, yeah. Yeah. So you should think of when I send a word, I'm actually kind of transmitting each letter individually, and then yeah, each of them can be corrupted. Any questions about this? Is the setup okay? So yeah, you want to make as many words as you can, such that none of them can be confused. So your answer, so if this graph has no edges, then the answer is going to be n to the k again, right? But now if you have an actual graph there, it's going to be a more complicated problem. Maybe let's think of an example where, let's say, what if I'm just thinking about words of length 1? And maybe we can even think of this specific graph G or something. So if I'm trying to design my language to have as many words of length 1 as I can. A word of length 1 is just one letter, right? How many words can I take? Yeah, 2, yeah. So what if, but now, so yeah, I guess now what's the kind of relevance of 2? So now suppose this is a general graph G. How many letters could I take? Yeah, exactly, right? Because yeah, a bunch of words of length 1 that are can't be confused is just the same thing as an independent set. So the answer when k is 1 is always going to be the independence number of G. Okay. So in some sense, independence numbers kind of come into this. So now what I want to do is say, okay, what about higher lengths of words? And I want to represent that as the biggest independent set in a different graph, sort of a graph that is kind of related to G in some way. Actually, if you think about it, though, it's kind of clear how to construct this graph, right? Just take all of the words of length k, all of them. If 2 words can be confused, put an edge, because I'm not allowed to take both of them, right? So, for example, for the length 3 words, there would be an edge between, like, I would have 5 to the 3 vertices. I'd have an edge between these things, and all the different pairs that can be confused. And then all I would be doing is finding the biggest independent set in that graph, because I want a bunch of words that cannot be confused, right? Let's make it more formal, though, and like have some notation to talk about this type of a graph. So this turns out to be related to something called the strong product of graphs. So for graphs G and H, the strong product of G and H is the graph. So the notation is G, like with a square with a cross in it, and then H. if you draw a few examples, you can actually kind of see why this is the notation. But we'll do an example in a second. But let me just say what this thing is. So it has vertex set V of G, the Cartesian product V of G cross V of H, where so this is the vertex set of this graph. And now I have to describe what it means for a pair in here to be adjacent to another one. So UV is adjacent to, let's say, WZ if, so there's going to be kind of three conditions. So the first condition will be that, so this pair is adjacent to this one if U is adjacent to W in G, and if V is adjacent to Z in H, or U is equal to W, so these are actually the same vertex of G, and VZ is an edge of H, or thirdly, you could have UW G and V is equal to Z. Okay, it's kind of a mouthful. But the point of this strong product is that this is sort of the right thing for encoding like words that can be confused. So let's say I take the graph G and then I look at the strong product of G kind of times itself. The elements of that, the vertices of that graph are kind of pairs, right? Where pairs of letters, which is the same thing as a word of length 2, right? I could just write this as concatenating these two things. So a pair of vertices of G, so let's say I did G cross G, right? The strong product of G with itself. This would be like a word of length 2, and we're saying they're adjacent if the first letter of this one can be confused with that one, and this one can be confused with that one, or if the first letter here can be confused with that one, but, these two letters are the same and these ones can be confused, or these ones can be confused and these ones are the same. Which is exactly, so these three conditions are kind of encoding the idea that like we're talking about. And more generally, if I apply this product over and over, that gives me it kind of encodes words of length k that can be confused. So what we want to do is basically take a graph G and multiply it by itself with this type of product over and over and over. So let's say we let G to the 1 be the graph G, and G to the K be G to the K minus 1 strong product G for each K at least 2. So then the max number of words of length k that we're allowed to take in our language is just going to be the independence number of g to the power k. Okay. Maybe let's go back for a second and do an example with this strong product just to see how to think of it. So right, let's say G is this graph, and let's label the vertices, I don't know, 1, 2, 3. Okay. If now I'm doing G cross G, the vertices are all the pairs like 1, 1, 1, 2, 1, 3. So none of them. 2, 1, 2, 2, 2, 3, and then 3, 1, 3, 2, 3, 3. Okay. And if we think about the adjacency relation, so one way you could be adjacent in this graph is you could have the same first coordinate and be adjacent in the second coordinate. So that kind of means within any kind of column, the graph I get should be the graph G. Like if I fix the first coordinate, the second coordinates kind of they kind of induce the graph G, right? Because one of my constraints is or my conditions is you could have the same first coordinate and be adjacent in the second. So basically to make this graph, you put a bunch of copies of G in the columns, but then the same thing is true for the rows. Put a bunch of copies of G in the rows. Okay. So that's kind of dealt with these types of edges, the second and third conditions. And then we just have to think about this first condition, which is like, for example, 1, 1 should be adjacent to 2, 2, because these can be confused, right? So it gives you these like x's, kind of like this. Okay. So the fact that this is a bunch of squares with x's in it, I mean, that kind of, that's the type of picture you're often going to get with this product, and that kind of inspires the shape of the of this thing here, right? Basically, if you took K2 with itself, it would literally look like this picture. Like that would be your graph. That's why that's the symbol. Okay, any questions about this? Okay, so let me now define something called the Shannon capacity. So we're interested in the independence number of G to the K. But let's try to think of this as make this into a sort of asymptotic problem where we're kind of interested as, with K going to infinity. Although if K goes to infinity, this number is just generally going to go to infinity. But it becomes natural to take the 1 over kth power. So the Shannon capacity of G is the limit as K goes to infinity of alpha of G to the K to the 1 over K power. Oh, and the notation is theta of G. So this limit is, the symbol is theta. Okay. in some sense, you should think of this as like the effective number of letters in your alphabet. Because remember when we did at the beginning, when we had no edges in the graph, like the number of words was n to the k. So if you have n letters in your alphabet, you had n to the k different words. Then you take that to the 1 over k, it gives you n, which is the number of letters. So like when you have no edges in the graph, like this is just giving you n, which is the number of letters. So you can kind of think of this as like sort of asymptotically, this Shannon capacity tells you effectively sort of how many letters does your alphabet really have. Although this is not going to be an integer typically. But any questions about this definition? One possible complaint, though, I mean, at this point, is I'm writing a limit, but like, how do you know it converges? So that's what we're going to prove in the rest of this class, is that this thing does actually converge. Okay, so at the moment, this definition looks like it might not be well defined, because, yeah, if I just take a sequence of numbers, there's no guarantee it's going to converge. So one standard way that comes up a lot, if you want to show a sequence of numbers converges, probably the simplest way, I would think, is like, I don't know, show that it's monotone and bounded or something. Like if it's always decreasing or always increasing, and it's bounded between, here and here, it has to converge. Monotone convergence theorem or something, right? But here's the issue here is that actually this sequence, so you can come up with some examples to show that this is not monotone. Okay. So that kind of rules out one approach to showing that it converges. It is bounded, though. That's one thing. So I think this is in your assignment, so I won't prove it here. But in general, if I take two graphs G and H, if I look at their independence numbers, so if I take the product of the independence numbers of G and H, that's at most the independence number of the product of G and H, which is at most the number of vertices of G times the number of vertices of H, where this upper bound is kind of trivial. I mean, that's just how many vertices this thing has. So that's one little thing on your assignment that shouldn't be hard. But what this tells you is that, for example, so therefore, kind of as a corollary of this, this should be at least this, and that should be at most the number of vertices of G's. So this thing is bounded, but it's not monotone. Okay. Have any of you heard of something called Feketei's lemma? No? It's a nice little thing that's sometimes quite useful. It's useful because it's pretty widely applicable, I guess. So that's what we're going to use to show that this thing converges. We're going to use Feketei's lemma. So before I can state it, I need a definition. Say that a sequence let's say A1, A2 dot 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 is, so let's say it's sub-additive. If A sub n plus m is at most an plus am for all n and m, at least one. Superadditive, if it's basically the same thing, but the inequality goes the other way. So all of these things are for all n and m, right? If it satisfies so this kind of relation. Let's say submultiplicative. If an plus m is at most an times am. And then let's say supermultiplicative. It's basically the same thing, but the inequality goes the other way. Okay, the reason I mention all four of these things is because Feketay's lemma is sometimes written for, sometimes it's written for these kinds of sequences or these or these or these, but like all of them, like Feketay's lemma for any of these four kind of situations, it's the same lemma. Like, I mean, the same proof. It's all kind of the same, but you just have to kind of change things a little bit. But yeah, it applies to all these situations. So what the lemma says, so I'll just write it for, I don't know, subadditive functions. So if A1, A2, dot, dot, dot is subadditive, then if I take the limit as n goes to infinity, or let's say k goes to infinity, sorry, of ak divided by k, so this is equal to the infimum over all k of ak over k. Okay. So in particular, what this is saying is, like, this is saying the limit is equal to something. Like this, so it's not the limit of the AKs, but it's like the ratio AK over K. But in particular, this, like, if this is true, it implies the limit exists, right? So it's saying the limit exists. And in fact, not only does it exist, it's just equal to this, the smallest, I mean, the infimal possible value of this ratio. But one thing to note is that it's possible that this ratio, like this could be unbounded below. So this, so it could be, like in general, this could be, like the limit could be negative infinity. So like this limit exists. It's always either a number or it's negative infinity. Okay, but if your sequence is bounded above and below by something, then yeah, it won't be negative infinity, right? Okay. It's not hard to prove this. it's kind of a nice proof. It's kind of surprising to me how it works, but I maybe won't focus on proving this, and I'll just kind of apply this. So this is for subadditive sequences. If I wanted to do superadditive, I would just change the inf to a sup. It's kind of not hard to see that that's going to be the same thing. And now if you wanted to go from additive to multiplicative, you could just do things like take logarithms. So if I have a sub multiplicative function, let's say, and now I define another sequence, which is the logarithms of these, then it will, like, multiplication turns into addition when you take logs. So it'll just become sub-additive. And then you just have to think of what that does to all of this. So kind of a corollary of this, if you just turn this into superadditive and then turn it into super multiplicative, is that if A1, A2, ... is super multiplicative, then the limit as k goes to infinity of ak to the power 1 over k, that turns out to be the right thing when when you kind of take logarithms. Like if I take the log of this, the 1 over k will come out in front. So this turns out to be the right thing. And since we're doing super multiplicative, this should be the supremum of ak to the 1 over k. Okay. And it could be infinite, or it could be a number, right? But either way, the limit kind of exists. Well, the limit exists, and it could be infinity, right? So yeah, I guess what I'm saying is it's not hard to transform this statement into this statement. Questions about that? Okay. Okay, so let's use this to show that the Shannon capacity exists. Actually, it kind of boils down to this lemma again. So I guess a sort of claim is that this Shannon capacity is well defined. Meaning that the limit always exists. And, well, let's just show that it's super multiplicative. So what I mean is, so kind of take the sequence, well, consider the sequence alpha g to the 1, comma alpha g squared, right? All these independence numbers of powers of g under the strong product. By this lemma, I know that alpha of g to the n plus m, well, g to the n plus m, if you think about it, it's not hard to see that this product is like, I don't know, associative, and I mean, it has various nice properties. So I can write this graph like this, and by this lemma over here, this would just be alpha to the g, alpha g to the n times alpha g to the m. So I'm just using this lemma where instead of g, I put g to the n. Instead of h, I put g to the m, right? I'm using this lower bound. So what this is telling me is that this sequence is supermultiplicative. So by Fekette's lemma, the second version there, the limit exists. Okay. And it can't be infinity because we know that for every k, this number can't exceed the number of vertices of G. So when I say the limit, I mean the limit of alpha gk to the 1 over k, right, exists. So this is just, yeah. This is the kind of right thing. And then, yeah, it is going to be at most v of g. So it's not infinity. Okay, so the Shannon capacity exists, and it always outputs a real number. Okay. Any questions about that? Okay. Here's a kind of deep and interesting question. Suppose I give you a graph G. Are you guys, how familiar are you with like computer science, like complexity problems, like decision problems and things like that? Have you heard of, say, MP complete problems? No? Well, a very quick crash course is, suppose I give you like a decision problem or an optimization problem is generally like, suppose I give you something like a graph and I want to say, I don't know, what's the big size of the biggest independent set, right? It's like some kind of algorithmic problem. You want to compute some number related to that graph, or what's the chromatic number, blah, 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 right? Suppose I give you a graph and I say, please run an algorithm to determine the Shannon capacity of that graph. Like, actually, it's an unsolved problem to determine, does there even exist an algorithm that runs in finite time for every graph? So I guess a sort of open problem. Is there an algorithm to compute the Shannon capacity? Note that like this is a different thing than other types of problem. Like, I mean, for example, if I give you a graph and I say, please output the size of the biggest independent set, it is kind of clear that there is an algorithm. Like it may be very slow, but there is an algorithm. I could try every subset and then just take the biggest independent one, right? This is a different beast, right? Because if I want to know this number, in principle, I may need to compute the independence number of this, that, which goes on forever, right? So it's actually not even known if you can even compute this in a finite amount of time. An even crazier thing is for very simple small graphs, we don't even know the answer to this. So another open problem, what is the Shannon capacity of a 7-cycle? So if we had an algorithm to compute this for every graph, surely 7 vertices, like a 7-cycle, super symmetric, nice graph, like we'd be able to compute it. But yeah, we can't even compute this. So it's a very difficult problem to compute the Shannon capacity of a graph. We don't even know how hard it is. Like it could be that there's no algorithm that can even do it. So what we're going to prove next time is a kind of fantastic theorem of Lovász that the Shannon capacity of a 5-cycle is equal to the square root of 5. I don't know, maybe I should have made you try to guess what it's going to be. I feel like that's not that guessable. Okay. Yeah, so to prove the lower bound is kind of the easy part. So the Shannon capacity is going to be, by Fekette's lemma, because Fekette's lemma gives us this very specific value for the limit. It's the supremum over all of these things. So if I just plug in, for example, k equals 2, that gives me a lower bound on the Shannon capacity, right? Because the lower bound is the supremum. So the lower bound is not hard. It's at least, so if I take C5 squared to the 1/2, like, so this is, yeah, this is just taking the second thing in the sequence. Yeah, this sequence where I'm taking the 1/k powers. And it turns out that the independence number of this thing is 5. Okay. In fact, there's another assignment question for assignment 6 where yeah, you're going to prove a more general version of this. So this gives you a lower bound of square root of 5, right? Because if I plug in 5 here, it'll be the square root of 5. Right. So the hard part is to show that the Shannon capacity of C5 is less than or equal to square root of 5. Okay, and that's going to be the kind of main focus next time. Okay. Again, going back to how you should interpret this number, right? This is kind of saying if I wanted to have, if I wanted to develop a language of code words where I've got 5 symbols with this kind of relationship of, you know, which symbols can be confused with which symbols, like kind of as k, if k is very large, then you should think of it as like effectively the number of letters in my alphabet would be root 5. Which is a strange number of letters to have in your alphabet. But that's kind of the idea. Any questions about any of this? Okay, yeah, so the next time we're going to try to prove this.